And you explained to me, and I've said it here, that there are ideas percolating that the fabric of space-time might be woven by wormholes that connect the virtual particle pairs that come in and out of existence. And that if they're connected by wormholes, rather than just some field, then the wormhole is an actual structural texture of the universe.
Yeah. In fact, the other way.
Now I'm sorry.
What?
First of all, I need some weed to even deal with this. Because if I'm trying to figure out what you just said here, because it's so freaking, I mean, it really is just crazy.
Wait, let's back up. The vacuum of space is not a vacuum.
Right.
Because quantum physics requires what?
There's all sorts of uncertainty, and that uncertainty means that there's fluctuations, and therefore there are particle-antiparticle pairs, there's energy fluctuations, there's field fluctuations.
Right.
It's a roiling mess out there in empty space.
So there's no nothing.
Yeah.
There is no such thing as nothing.
That violates uncertainty if it was truly nothing.
Right. If there was truly nothing, we couldn't have uncertainty.
Yeah.
So the uncertainty is, gives us the fact that we do have virtual particles.
Yes.
We know that they pop in and out of existence. Well, what you're trying to tell me?
I think it's not that we know they're there. No one denies it because it's completely consistent.
Well, I'd say the Casimir force, where you actually put two metal plates in otherwise empty space, they should simply sit there. They're drawn together, and our best explanation is it's the virtual pairs of particles. It's the fluctuating field.
I didn't. I feel like I have fallen into a Star Trek nightmare.
So you take two exactly parallel plates.
Okay,
and evacuate what's in between them.
That makes sense.
The best vacuum you can muster. Then you slowly move them together.
Right.
There is a point within which a whole other force kicks in.
That's right. And it's not the gravitational force.
It's not
the electromagnetic force. Rather, it's a force that comes from the Casimir field, which is basically...
That got a Nobel Prize, the Casimir?
1948 is when it was discovered.
Okay.
It got one in my book.
But it should have.
You just gave it one.
I just gave it one.
Yeah, it definitely deserved one.
That's insane.
But it's an imbalance between the fluctuations of uncertainty within the plates and the fluctuations of uncertainty outside the plates.
Oh.
And it's that imbalance.
Creates a force and puts them together.
Yeah.
Okay. Okay. So that's how we get the particles in the vacuum of space. Okay. So now,
unbelievable.
So now, what compels you to say wormhole rather than just a field?
Right. Well, because it really comes from the idea of quantum entanglement. What we find is that entanglement, which normally we think of as particle pairs, but now we're finding that the vacuum of space may be stitched together by the threads of quantum entanglement itself. So deep down within the substrate of reality, it may all be stitched together by quantum entanglement. And then other work shows us that quantum entanglement connecting two particles is just like a wormhole, going from one to the other.
Because what happens in one happens to the other instantly.
Yes.
And that means they're touching each other in that instant.
Connected in some weird way. And entanglement is one language, but we believe wormholes may be the general relativistic version of that quantum language.
So it's like a little quantum net holding the whole universe together.
Exactly right. Because we find mathematically, if we cut the threads of quantum entanglement, which we can do mathematically, space falls apart. It discretizes into little tiny pieces and then just disappears.
I gotta go.
No, Chuck. I need you to the end of this. Chuck, don't leave me. Don't leave me, Chuck.
Oh my God. Dude, that's insane.
It's not just that there's a field there. It's the fact that they were quantum entangled that makes the wormhole model compelling.
Yeah, but I would say you don't even need the particle pairs. It's as if the entanglement is entangling regions of space. So space itself has a fundamental substrate woven by these threads of quantum connection. Now, look, it's mathematical, but it comes out of our cutting edge ideas. It all makes sense.
It just makes sense.
He's saying he's not pulling it out of his ass.
Right.
Okay. He's saying the math gave it to him.
Works.
And he started out saying my boy loves the math. So now, last thing.
Yeah.
Explain why you need more than 4 dimensions for your string theory universe.
Well, it's a very concrete explanation. when we look at the equations of string theory, there's a consistency equation where something must equal 0 or the math doesn't work. That something is a product of two things. One term is really complicated. It's never 0. The other term is the number of dimensions minus 10. The only way to get it to be equal to 0 is for D to be equal to 10. That's it. I am not joking. This is where the constraint of extra dimensions comes from in string theory.
The math is forcing our hands.
Forces your hand. And then you say, well, let me take this math seriously. One thing you could say is, well, if it's not D equals 4, 3 space and 1 time, throw the theory away. Others of us will say, hey, let's consider the possibility.
Don't sell the universe short.
Yeah, exactly. So why should these 3 dimensions of space be the only ones?
Right.
We only are aware of them because they're big enough that we can be directly aware of them with these really faulty sensors that we have.
Right. If it's only your senses that limit that awareness,
Yeah.
why not, in principle, can we build something that can gain access to these higher dimensions?
Yeah, so there are experiments on the table. Some have been carried out, but more precise ones may be done where you study Newton's law of gravity. Why does Newton's law go like 1 over r squared? Why do we teach our kids GMM over r squared?
It's a geometric
sphere in 3 dimensions of space.
Yes.
Look at that sphere in 4 or 5 or 6 dimensions, and the 2 in Newton's law won't be a 2.
No.
It'll be a bigger number. The fall off will be differently.
Right.
And so look at the gravitational force on very small distances. Look for a deviation from the 1 over r squared that Isaac Newton told us about in the late 1600s.
Okay, because that's only in our dimensional measurement of it.
Yes.
Okay, because I'd asked you, again, over that same lunch.
Yeah.
Why did we have lunch? I forgot. We were just
We were
catching
hungry.
up. No, we were just catching up. You know, it's my annual fix, my annual Brian Greene infusion. It was, could dark matter be ordinary matter with ordinary gravity in a parallel universe? Because for reasons I don't understand the math of, the field theory equations of, you were telling me that electromagnetic energy cannot escape our space-time, but gravity can.
In a certain model called the brain universe, where our universe, B-R-A-N-E, it comes out
As
of
in
string
membrane.
theory. Yeah, it's a membrane. So our universe is like a 4-dimensional membrane floating in a higher dimensional universe that might have other membranes.
Higher dimensional membranes.
Yes, and those other membranes like parallel to us, like 2 slices of bread and a big loaf of bread.
I like it. So so one slice of bread is some other membranal universe.
Yeah.
Ours is this one, but it's one multi-brain.
Yeah.
Okay, and so gravity could leak out of one into the other.
Or it could just be yeah, that's right. So
But
the
that's what I'm
gravitational
getting.
pull. Yeah,
That's what I'm getting.
Yeah.
So if the other universe has 6 times, nobody, see, this is where you corrected me. Because I was thinking, because we have 6 times as much force of gravity operating in the universe as matter and energy can account for it.
Okay.
Factor of 6.
Right.
So I was saying, why isn't it just a parallel universe that has 6 times the mass, and it's leakage into our universe, and we're trying to feel the elephant, trying to figure out what it is, but it's just regular matter in another universe whose gravity leaked. But then you said, if it's in another membrane, it's going to be dropping off faster than 1 over r squared.
Yeah.
Like 1 over r cubed, there's some higher dimension.
Yeah.
And if that's the case, it has to be way more than 6 times.
But you could imagine rigging it so that it would have the right amount.
Yes.
And people have studied this, and it's hard to make these theories work in detail.
And be all
But in
self-consistent.
principle, it's an idea that's absolutely worthy of investigating, because that's one way to make it invisible. Just put it in another
Just stick
membrane.
it somewhere else.
Yeah, exactly.
And then
exactly.
and then where we can still calculate with it, it's
Yeah.
not a problem.
Yeah.
Right.
Yeah.
That's crazy.
Man.
Oh man.
All right.
I don't know what to believe about anything. Nothing is real. Nothing is real, man.
Dark energy. I'm curious about this because it was a natural arithmetic element of Einstein's equations. It's like an integration constant, as I understood it.
You talk about the cosmological constant?
The cosmological constant in his equations that enabled Lemaitre to calculate that the universe is either expanding or, well, the universe is not static. And so there's a term there. And if you've had calculus, you might remember there's a constant of integration. Often it's just 0 and you can ignore it. But when we were in graduate school, I'm a little older than you, when we were in graduate school, we always recognized, we paid homage to that constant, but said, let's assume it's 0. If this term existed, it would mean there was a force operating in the universe opposite that of gravity.
Depending on the sign of the cosmological constant, but yes. Because it could have either sign.
Okay,
yes.
It would either work with gravity or against
exactly,
it. Okay,
exactly.
But if we had a static universe, it would be something just holding up the universe against the collapse of gravity.
Which is why Einstein thought of it.
And we didn't have any reason to think it, so it could be zero. And but we always had to go through that portal. We say, here it is, we set it to zero and move on.
Exactly.
Okay, then it gets discovered.
Yeah.
Okay, dark energy gets discovered in 1998, gets the Nobel Prize, using quantum physics, which has done so well by us.
Yeah.
Perhaps the most successful theory ever about anything, fails in its attempt to predict the amount of dark energy in the universe.
Yeah.
And it fails badly by a factor
What's up with that, Brian?
of a Google.
Wow, by a factor of
bigger than a Google. 10 to the 10 to like it's like 10 to 123 or something.
Google is 10 to the 100th?
Yeah.
It gets the wrong answer by the biggest amount ever in a mismatch between theory and observation.
Yeah.
Where are we with the dark energy theorists?
Well, look, what this is showing us is that quantum mechanics is incredibly successful when you apply it to the electromagnetic force, to the weak nuclear force, to the strong nuclear force. But we've long known that when you apply it to gravity, something goes wrong, something changes. This is the motivation for string theory, and this is the motivation for trying to go beyond conventional approaches. And so you're absolutely right. This is the clearest signal that something is wrong. Now, here's, I think, our best guess.
That's not something's wrong. That's actually a good thing.
Well, it's an opportunity.
Yeah. Opportunity.
Yeah,
that's the way.
Yeah, it's a huge opportunity.
Yeah, the press always says, oh, scientists are angry or this. No, we're delighted.
Yeah.
If something breaks, oh my gosh, it's a new thing.
Yeah,
That's
exactly.
right. That's right. And so I would say my guess where we're going is, and many of my colleagues agree with me, that you can't quantize gravity the way you had to quantize Faraday and Maxwell's electromagnetism, or the way I had to quantize the weak or strong nuclear forces. It may be that gravity and quantum mechanics are already so intimately connected that it's a completely different mindset when you approach them. You don't take the rules of quantum mechanics and slap them onto gravity. That gets you the wrong answer. That's the wrong approach. In fact, this idea of entanglement and wormholes suggests that gravity and quantum mechanics, they're already in there. They're already there.
That makes sense.
They already have the shotgun wedding.
Exactly.
You just was in the tent.
Exactly. So you just need to understand that melding better. And when you do, perhaps you'll be able to do a calculation of the cosmological constant and get the right answer.
Right.
Yeah. Now, another answer might be maybe the cosmological constant is not a constant. Right? There's recent
They're working on that now.
Yeah. Right. Maybe it's changing over time. And so you don't actually calculate the number. You just need to understand the dynamical process.
However, doesn't the math in general relativity require that it be constant?
No.
That's how it came out of the integral.
There can be a constant, but it doesn't have to be the only contribution that looks like that constant. And the other contribution can change over time.
What do you say there?
It can be a constant,
but
it doesn't have to look like, and then...
No, it's not the only contribution to that term.
Right.
So you can have a field that slowly varies over time. And that field may dominate this
So that
contribution.
field is meta to that equation.
Yes.
Look at that.
It is
my
meta
God.
to that equation.
Oh my
Absolutely.
gosh.
So Einstein did not talk about that
No, he
field.
didn't. No, he wasn't there
and
yet.
You're right. And he did talk about the constant because you're right. It's just an integration
It's
constant.
an integration
It's
constant.
right there.
It's a constant. It's
Yes.
a constant.
Yes.
So if in fact it needs to modify, because that's how they reconcile this tension in the age of the universe.
Yes.
Because the age of the universe, in my day, we didn't know it by a factor of 2. Right. Now people are, there's a 10% difference.
So it's more than 6,000 years. Is what you're saying.
Yes, that's exactly what I'm saying. Yes. When Noah's flood took place. So to relieve the tension, as we describe it, this was a 10%, some single-digit percent. Uncertainty in the age of the universe. Actually, not uncertainty. These two methods have very small, tight uncertainties that do not overlap.
Yeah.
That's why everyone is freaking out. And as I learned recently, you can resolve that by allowing the cosmological constant to vary in some way, but that's a meta variation on top of Einstein.
Yeah, no, this Hubble tension that people are struggling with today is exactly something that also may point toward a dynamical value. So we'll see.
Right.
But yes, the true test of a version of gravity that you fully understand with quantum mechanics included would be a calculation of the cosmological constant and get
Are
a number.
you and your
Yeah.
people smart enough to get this figured out?
I don't think so.
And that's our show. Good answer. Because I've dragged you over the coals
We
about
have come
that.
full circle.
Because I've told him, I said, look, Einstein came up with general relativity in 10 years by himself. You string theorists, there's dozens of you been working on this for decades. Either you're all wrong or you're all just too stupid to figure it out.
And it's probably a combination of both.
Love you, man. Brian, thanks for coming back.
My pleasure.
To Star
Thank you.
Talk. Always good, Chuck.
So great.
Chuck, we'll find you in the hospital.
Bless you will. I'm completely fried right now. I am fried.
Just to take us out, let me remind us all, we are in my office at the Hayden Planetarium of the American Museum of Natural History.
The Cosmic Crib.
The Cosmic Crib. And after this conversation we just had, I delight in realizing and celebrating the fact that just a few pounds of organic matter inside of our heads can not only contemplate, but figure out how the universe works. And yes, we still have a long way to go. And we don't even know how long a way to go remains in front of us. But the distance we've come thus far gives us everything that we call civilization. And it's the power of mind over the mysteries of the universe. And that is a product of the eternal curiosity expressed by our species, beginning in childhood, continuing for some into adulthood. We call them scientists, those who never lost that childhood curiosity. Brian Greene, of course, among them. So I'd like to just give a shout out to our species for all that has wondered as we looked up at night, all that we have discovered, and all that we have yet to figure out. That is a cosmic perspective.